Good morning for you chemistry students, or whatever time it is. Some of you I know have been keeping very strange hours. All right, so in our last lesson, we established that there are both strong and weak acids and bases. And in both cases, if it is a strong acid or base, what that is telling us is that it essentially 100% ionizes or dissociates into ions. Okay, so weak acids and bases only partially ionize, and therefore the pH is, not nearly as strong of an acid or as strong of a base when we're done because we don't have as many hydrogen ions or hydroxide ions. So some common weak acids that you should be familiar with are, from our organic unit, all carboxylic acids. So this one here is methanoic acid with one carbon, but all of the carboxylic acids are weak. And then here's a few other ones. So hydrofluoric acid, carbonic acid, sulfuric acid, sulfurous acid, and nitrous acid. Okay, sorry, that was hydrosulfuric acid. All right, so if we want to know how much an acid ionizes, we can get a percentage. So it's very much like a test mark where we're saying how many ions we end up with compared to the original full concentration of the acid that we started with. So this would be at equilibrium. So an example calculation, figure out the percent ionization if you have 0.1 mole per liter methanoic acid, and at equilibrium the pH is now 2.38. So always a good idea to just write down, before you start, what is it you're trying to get. So we're trying to get the percent, and we'll use this formula up here. We are given the concentration of the original acid, and acids we often just write HA because there's always going to be a hydrogen. We could just put methanoic acid there as well, but this is fine. So 0.1 moles per liter. And we have been told the pH is 2.38. So also in our previous lesson, we learned that you can take pH and figure out hydrogen ion concentration, which we are going to need. So hydrogen ion concentration is going to be 10 to the negative pH, which is 10 to the negative 2.38. And when you use the second function of your log button on your calculator, you should get 4.2 times 10 to the negative 3 moles per liter. So when this acid has reached equilibrium, this is the very, very small concentration of hydrogen ions that we have compared to the original concentration of the acid. So you can see that it's just a very small amount. So now we have everything we need to plug into this formula. So hydrogen ion over original acid concentration all times 100 because it's going to be a percent. So 4.2 times 10 to the negative 3 moles per liter divided by 0.10 moles per liter all times 100 is going to give us 0.042 times 100, or 4.2% ionization. That is not very much. So that tells us that it is a very weak acid because 96% are still full acid molecules. Okay, so 96% are molecules still, and therefore not affecting the pH. Okay, so that is one type of calculation and gives you just a better understanding of weak acids. So we have a constant, an equilibrium constant, that is used to describe how much different acids ionize. So of course it's K, and we put Ka for acid. If you check your textbook, page 803 has a great big chart full of various acid ionization constants there that you can look up when you're doing problems. Okay, so if we think of what's happening when the acid ionizes, we start with our acid, of course, and you can think of it as, the acid is put into water, which is a liquid. And then the acid gives up its hydrogen to the water, so we actually make hydronium. And then we also have just the leftover, whatever anion that was. So this reaction is usually shortened and just written like this, because we don't worry about writing down the liquid because there is no concentration. And we know that hydrogen ion and hydronium ion are just equal because the hydrogen is always going to find a water to react with to make the hydronium ion. So this is just simplified. And by getting rid of the water right here and simplifying it, when you write out your equilibrium law equation, just like we have been previously, you're going to take your products, raise them to the exponent. So we've got the hydrogen, imaginary one, and the acid. Okay, so we don't have to write the 1 if we don't want. Okay, so the next problem we're going to do, we're going to be using that formula, and we're going to solve a Ka value for hydrofluoric acid, which we could look up, and we will look up after this to check to see how we did. So we're going to start with a 0.1 mole per liter solution, and at equilibrium, you're told what the hydrogen ion concentration is. Okay, so it's a good idea to start with a rice table, because we have one value here at equilibrium, but we're going to need all of the values in order to solve for Ka. So we'll put this into a rice table, and we've got hydrofluoric acid, and it's turning into hydrogen ions and fluoride ions, or hydronium ions if you prefer. Okay, so initially we're going to start off with 0.1 moles per liter, and we're not going to have any ions initially. As it starts to change, which means as it starts to ionize, we're going to lose molecules of acid. How many? Just 1x. And we're going to be gaining ions. So plus 1x, plus 1x. This should look very familiar. So at equilibrium, we're going to have 0.1 minus x. We're going to have x, and we're going to have x. However, look, they told us that the hydrogen ion concentration was 0.078. So x is equal to that. And therefore, we can sub that in. So x over here is the same value, obviously. And over here, if we sub 0.1 minus 0.0078, and this is going to equal 0.0922. Okay, now we have all the concentrations at equilibrium. This is our equilibrium law equation up here. So now we can solve for Ka. Let's see how much more room I have here. Shouldn't be too bad here. Okay, so Ka is going to be hydrogen ion times fluoride ion, all divided by the concentration of HF at equilibrium, remember? So we're going to have 0.0078, and these are just raised to the 1, times 0.0078 divided by 0.0922. Okay, and if you do that carefully on your calculator, and we're going to go with 2 significant digits, so I think it's 6.5 something, 659, I can't remember exactly. Okay, so we're going to round it to 6.6 because we had 2 significant digits here. Here we had 3, so we're going to keep the least. And that is going to be the Ka value for the acid hydrofluoric acid. So if you check on page 803, oops, check page 803 and the Ka matches. Okay, so we have done that correctly. All right, so in this question, we started with a hydrogen ion concentration and we were able to solve the Ka for that particular acid. I could have also added an extra step. I could have started by giving you the pH, but that would be no big deal because you have a formula where pH is negative log of the hydrogen ion concentration, so we could have just done that extra little step there. Once you have H+, you can see that that is going to be equal to X in your Rice table. And once you've got all your equilibrium lines solved, you can then plug into the equilibrium law equation and solve for Ka. So this is kind of the general process that we went through or could go through with a question like this. This one was just a little bit easier. Okay, so now we're going to go backwards. So we're going to do the same type of question, only we're going to work in the opposite direction. So this is calculate the pH of a weak acid, and they're going to give us the Ka value. So essentially now we're starting with the Ka value. From that equilibrium law equation, we are going to be able to solve for X, which we know is going to be equal to the hydrogen ion concentration. And then, of course, you can figure out the pH using your formula, because pH will be pH will be negative log of the hydrogen ion concentration. Okay, so once again, we're going to start with a Rice table. So it's acetic acid, so this is ethanoic acid, okay. So, HC2, H3O2. Okay, and that's going to, of course, yield a hydrogen ion, which we really should be putting our states here. And the hydrogen that it loses is the one that was written at the front. And it's now going to have a negative charge because it loses an H+. So note, H is gone, now it's negative. Okay, so initially we've got 0.10, and as before, we have nothing at first. The change, as it ionizes, it's going to lose 1x. Oh, there's my dog. And gain 1x. So at equilibrium, we've got 0.1 minus x, we've got x, and we've got x. Okay, but we don't know x because we're working backwards now. So now we're going to have to get into some solving. Okay, so equilibrium law equation. Let's just get it set up and we will sub into it after. So Ka is going to be hydrogen ion multiplied by our anion. Okay, all divided by the concentration of the original ethanoic acid. These are all aqueous, otherwise they wouldn't be in our equilibrium law. And then you're going to look up the Ka value. These aren't a secret. They are all over the internet and in your textbook. So if you find acetic acid or ethanoic acid, go down, look up the Ka. You should be able to see that it is 1.8 times 10 to the negative 5. Okay, so now we have two things that are occurring at equilibrium. We've got everything in the E line of your rice table is at equilibrium, and Ka is the equilibrium law, so obviously it's at equilibrium. So we're going to substitute the E line into this formula. Okay, so 1.8 times 10 to the negative 5 is going to equal x times x, because remember these are just raised to the 1 in this particular example. And it's going to be all over 0.1 minus x. Now, when we do our algebra and get this all expanded, three things can happen, two of which we've seen before. You might end up with a perfect square that you can solve to get your x value. You might have to do the quadratic equation to get your x value, but more than likely, you're not going to have to get something that complicated because you're going to be able to do something called the 100 rule. And the 100 rule is used to determine if the Ka value is very tiny, that means the acid is very weak. It doesn't ionize very much, which means the change that happens going from when you first put your acid in the solution to at equilibrium is very minor. So x becomes a very small number, is what we're saying. Now, if it's a full value of x, even small numbers can make a difference. But if you're just subtracting x and it's really, really tiny, it becomes insignificant. So we're going to do a little check here to see if we can ignore that. That's what the 100 rule does. So we're going to check the 100 rule, and you will find with these questions that quite often the 100 rule is going to apply and get you off the hook from doing a complicated question. So the way it works is you take the initial concentration of the acid, you divide it by the Ka value for the acid, and if that number is greater than 100, you get to ignore it, because that is telling you that the change is so minor that like the decimals would be so tiny in your calculator, they probably wouldn't even like affect your answer at all. Okay. So for our question, we are going to do 0.10. We're going to divide by 1.8 times 10 to the negative 5. And if you do that carefully, you should get 5,555, which is much bigger than 100. Okay, so that is greater than 100. So therefore, we get to ignore the circled x. Not all the x's, but the one that is just being subtracted. Okay, so because of that, we're going to ignore that guy, which is going to help a lot. Okay, so let's rewrite this. So this is going to equal x squared divided by 0.10 instead. Now we're going to get rid of this on the bottom, we're going to multiply it up here, and we're going to have 1.8 times 10 to the negative 6, which is going to equal x squared. And now we have just something where we need to do our square root of it. So we're going to do square root of both sides to solve for x. And this will be 1.3 times 10 to the negative 3. And x is actually in moles per liter, right? Because everything in the rice table is actually in moles per liter. So that is x. Look back to your rice table. X is also the hydrogen ion concentration. Okay. So that is in our rice table. So we've now solved for a value of x. And the final step is figure out the pH, because that's what the question asked for. So pH is the negative log of the hydrogen ion concentration, which you practiced last lesson. And I didn't do a screen lesson, but I will just mention this now. If you remember from grade 11, that you do not need to put that negative into your calculator when you do this. I find it kind of messes a lot of people up if they do. So if you just kind of leave it out, at first you would get your final answer would be negative 2.89, but then you know that you need to multiply by negative, and pH values are 99% positive numbers. The other funny rule, which I'm not being picky about, but because we have 2 significant digits in our concentration of hydrogen, we should have 2 decimal places in our pH. So that was a rule that I mentioned in grade 11, and I said I'd be picky about in grade 12, but not this year. We're not going to be picky about that. Okay, so that is the 2 types of calculations you can do, which are just reciprocal of each other, where you can work from pH to Ka, or you can work from Ka to pH. Now, I want to mention that everything we just did could be repeated for weak bases, but we are not going to worry about that this year. It's very similar, just, new substances that happen to be bases, so bases that are weak, only partially ionized, but this time they're making hydroxide ions. What you'll find is that they're not things with hydroxide in them. So the sodium hydroxide, calcium hydroxide, etc. are strong bases. These will be usually things with nitrogen in them. So amines, ammonia, that type of thing are weak bases. So the base reacts with water. In this case, it accepts the hydrogen, so you end up with Hb+, and then you get your hydroxide ion. And then we can make a similar equilibrium law equation. And then essentially after that, everything we just did, because you're using this version, you're going to have hydroxide ion concentration that you're worried about, not hydrogen ion. You're going to be worried about Kb, not Ka. So it can all be repeated, but the questions I assign you today will just be with acids. Okay, good luck with your questions.